And very happy to have Amol Aggarwal from Columbia University, who will tell us about the Toda Lattice with the Soliton gates.
So thanks so much for coming and for the invitation. So as the title of this talk suggests, I will be talking about the Toda Lattice, which is an example of a Hamiltonian dynamic. Okay, so let me start by explaining what these objects are in a somewhat general context, and then I'll focus in on the Toda Lattice. So basically, by definition, Hamiltonian dynamics govern the evolution of a system of particles in some dimensional space as they evolve in time. So I'll denote the number of particles by n. I'll denote time by t, which will be non-negative, and I'll always be looking in one dimension, which is kind of rich enough. So you should imagine this is a bunch of particles moving around on R. So you can have a picture of mine like this, where here n is 6. So each of these particles will have a position and a momentum. So we'll let the ith particle's position at time t be q of it, and the ith particle's momentum at time be pi of t, and we'll define these bold-face p's and this bold-face q to be the vectors of positions and momenta that just put in all the particles together. Okay. So, so this is just set up. So you can think of the phase space of the system as telling you where all the particles are. So this is this bold-face Q, and where all their momenta are. So this is this bold-face T. So the space is basically 2 copies of R to the n. And in a Hamiltonian dynamic, what you're given is a map, a Hamiltonian, from the phase space, so Rn cross Rn, to the real numbers. Okay, so this is just some function h. And the evolution of these dynamics are given by the derivative of qi, so the evolution of the positions, or the p derivative of this Hamiltonian, pi derivative of the Hamiltonian, and the derivative of the momenta are given by the negative of the qi the negative qi derivative of this Hamiltonian. Okay, so this is all fairly general, but it's natural to take Hamiltonians that are of a specific type, and this type is still going to be quite general. So this type is given by where HPQ is given, the dependence on P is given by a sort of kinetic term. So you imagine pi squared, so that's kind of a kinetic energy, the sum of pi squared. And then you have a nearest neighbor term, which is V of Qi minus Qi plus 1. So what this is basically saying is that the local nature of the Qi, the way in which they evolve, only depends on the particle in front of Qi and behind Qi. So just Qi minus 1 and Qi plus 1 is going to be what's governing the derivative of Qi. Okay. So so now plug this into here, and the dynamics take a fairly concrete form. So the derivative of qi of t, well, you take this thing and you differentiate it in pi. So it won't hit this because, if it hits this, you'll get 0, and it'll only hit the pi term, which will just give you pi. So the derivative of position will just be momentum, which is of course what makes sense. And if you plug in this Hamiltonian into here, what you get is that the derivative of momentum is given by the difference of the derivatives in V's evaluated at the gap between the I minus 1th and ith particle and the ith and I plus 1 particle. So this is what I meant before when I said that the dynamics are sort of nearest neighbor. The instantaneous behavior of how the momentum is changing, the acceleration basically, of the ith particle only depends on the particle in front of it or behind it. Okay, so this is, again, a fairly broad class of systems, and a basic question you can ask yourself is, how do Hamiltonian dynamics with many particles behave after a long period of time under, say, generic initial data or random initial data? Okay, so what exactly I mean by this behave? This term behave can be taken can have many sort of precise meanings. For example, I might ask, how many particles cross the origin after a long period of time? Or what is the so-called 2-point function? So if I look in some interval, say between 0 and 1, what is the covariance between having a particle there at time 0 and having a particle there at time t? So that's kind of a mixing phenomena, how fast the correlations decay. You can ask all sorts of questions like this. You can also vary the initial conditions. For example, you can start from an invariant or stationary initial condition. You could start from something that's out of equilibrium. There are many ways in which you can make sense of this question, and all of them are basically interesting. So and very few of them are really understood. So now the one thing I should mention is that for me at least, the interesting regime, the regime that I'll be that interesting phenomenon will happen is when the number of particles, so I have two things here. I have a time thing that I'm kind of making to be big, and I have a number of particles that I'm making to be big. And you might ask, how exactly am I making them the two of them to be big? So the interesting regime is when the number of particles is at least or bigger than the amount of time you're running for. And the reason for this is fairly intuitive. If you imagine that time is much bigger than the number of particles, then what will happen is that after a while, since you're running for so long, the particles might start to spread out and they'll be really far from each other, and therefore they might not talk to each other anymore. So the interaction, which is kind of what's making this thing interesting, will kind of disappear. So I want to have the number of particles be kind of at least growing with the amount of time so that the interaction is never lost. So the interaction is kind of retained in the asymptotic limit. Okay, so this is always the kind of regime I'll be looking at. Okay, so now different behavior in this model is expected depending on the type of dynamics you look at. And by type will be extremely vague and what I mean by type. But broadly speaking, I mean, whenever you look at dynamical systems, it's kind of a dichotomy that happens, which is sort of an integrable system or an order system or a non-integrable or chaotic system, okay? And I won't exactly define what these terms mean. In fact, it's not sort of it's just a dichotomy, or if they're kind of there's kind of a spectrum between the two. Broadly speaking, integrable means that there are a lot of conserved quantities that sort of order the system, and non-integrable is kind of the opposite of that. But let me but the asymptotic behaviors of these two systems are believed to be fairly different. Yeah, please.
So what is time scale? I mean, because our number of particles depends on the unit measure. So you divide your time by some time scale?
Oh, okay. So let's say that each particle has unit velocity, like average unit velocity. So that basically fixes the time scale. So after time 1, each particle will move of order 1. Yeah. Okay. Yeah. Go ahead.
And how many dimensions are you?
One. So you could look at many dimensions, and this is interesting, but there will be enough richness for the purpose of this talk to stay in one dimension. Yeah. Any further questions? Okay, I will specialize further, but I'll start with this. Okay, so now, okay, this is a fairly broad question, and as you can imagine, it's been of interest as long as Hamiltonian dynamics have been of interest, which is over a century. And mathematical progress in the chaotic case has mainly been made under two modifications, which are sort of simplifications. Which is one is to sort of dampen the interaction, or sort of have some parameter that's tuning down the interaction. Another way of doing this is to kind of tune down the particle density, so you make sure that the particles are kind of somewhat spaced apart, so that, as I said before, the interactions between the particles become fewer and therefore get kind of weighed down. So you have kind of a parameter that you're tuning down that governs the interactions. And the key word, the buzzword nowadays that's taking off is so-called weak wave turbulence. So this is one limit or regime in which people have been able to analyze these systems. Another regime in which another modification that people have done is to randomize the dynamics. So I've randomized the initial data here by taking some random initial data, but what you can also do is you can drive the dynamics according to some additional noise. So like each step of the dynamics, you just add a little bit of randomness in. So you're kind of pumping noise into the system as it keeps going. Again, and the key word here is sort of the relevant buzzword here is the Carter-Précision or KPZ universality class that's believed to govern these systems. That's believed to govern the kind of non-random system, but that's been proven in many cases to govern the randomized, the stochastic system. So now both of these modifications are extremely rich directions of research. I mean, many papers have been studied on them, and vast kind of swathes of mathematics has been introduced under these two modifications. But my goal in this talk is to take an integrable system without any of these two modifications and try to say something about its asymptotics. Okay. So the integrable system that I'll be studying is a so-called Toda Lattice. So this was introduced by Toda in 1967, so 6 years ago. Okay, and the choice of V, so it's the same setup as before, and the choice of V is to simply take it to be exponential. So V of x is equal to e to the x. Okay, and I've written down I've just plugged in e to the x into the dynamics from the first slide. And okay, so once again, the derivative of position will be momentum, and the acceleration, so the derivative of momentum will be basically e to the gap between the particle and the particle in front of it, and minus e to the gap of that particle and the particle behind it. So you can think of this as a system of kind of cars moving on a highway, and the acceleration of the ith car it depends on the distance between it and the car in front of it, and then the car behind it. So that's not entirely unnatural.
Just to clarify, so your ordering of the QIs, that's
Yeah.
by position when you.
No,
say-
that's not my position. That's my initial condition. So I order them I pick some ordering arbitrarily, or you pick some ordering of the initial data, and then they evolve according to these dynamics.
Okay.
So it's very
You're
possible.
allowing collisions and you're allowing reordering.
Absolutely, that will all happen. Yes, yeah. Okay. Any further questions? Okay. So as a thing just to keep in mind, as you might imagine, this e to the gap, so e to the qi minus qi plus 1 will appear everywhere. So it's very convenient for me to just introduce this additional parameter a of t, which is the e to the qi of t minus qi plus 1 of t. And actually, it's also convenient to take the square root of that. So this object will appear every once in a while. Okay. So this is an archetypal example of a completely integrable Hamiltonian dynamic. So this is basically one of the first integrable Hamiltonian dynamics that was introduced. I'll explain the sense in which it's integrable later on. Okay, but just for the moment, maybe grant me that it's unequivocally in the integrable class from the previous slide. And this has been sort of intensely studied and appears ubiquitously in mathematics. So in addition to being a completely integrable system, which already has many mathematical aspects behind it, it appears elsewhere. For example, if you've ever diagonalized a matrix on a computer, you've probably used the QR algorithm to do that. And that's very closely related to the toda lattice. Another example where it appears in the context of dispersive PDEs, one of the basic examples of a dispersive PDE is the so-called KdV equation, and this is the very natural discretization of it. This is kind of the lattice discretization of it. It appears elsewhere, whether it be in integrable probability or in algebraic geometry. I mean, this toda lattice is fairly ubiquitous. Okay, so now I've told you the model, okay, but my previous slide both came up with the model and some random initial data under which to study it, okay? And I will study it under an invariant measure, so a stationary measure, which has the property that if I start out with this measure and I run the toda lattice for some amount of time, then I will still be under that stationary measure, so I will still have that measure is preserved under the dynamics. There are several invariant measures for the toda lattice, but there's one very convenient or natural one that people like, and that's the so-called thermal equilibrium. I will not justify this term. And it's where you independently sample the p's according to a Gaussian. Okay, I've ignored the constant. So the pi is distributed to e to the minus beta p squared over 2. Beta is some parameter that I have the freedom to tune. Okay, there's a constant in front to make this a probability measure that I'm ignoring. And the AI are distributed according to this called chi random variable. So I have a power of a, again, times the sort of Gaussian weight, dA. Okay, so these are, so I'm just independently sampling the p's and the a's according to Gaussian and these chi random variables. And I remind you that a is this. Okay? A is basically the exponential of the difference between the q's. Okay. So if I do that, then the claim is that this measure is preserved after I run the dynamic. And the proof is actually not very complicated. So I'll very briefly describe it, although I'll never use it, so you can tune me out if you want. So okay, if you plug in P and A, it's fairly quick to see that the distribution of, it's just a product measure. So the density of like the vectors P and A is given by e to, well, you can certainly see the minus beta p squared over 2 and beta a squared come in here, and then you'll have this sort of factor come in here, a number dp dq. When changing variables from a to q, you actually remove this minus 1, okay? And so this is just a rewriting of this invariant measure. And the point now, the reason why this is invariant is twofold. So first, the Liouville theorem will tell you basically under a Hamiltonian dynamic that the Lebesgue measure is conserved. So dp dq is preserved. And what I also know, again, just a basic fact, a fact quickly verified, this is not a deep fact at all, about Hamiltonian dynamics is that the Hamiltonian itself is conserved. So this HPQ is conserved, which I remind you is this pi squared over 2 from before. And this AI squared is exactly this guy over here. Okay, so this term is conserved under the dynamics, okay? And this is conserved. So at least if theta equals 0, hopefully you believe me that it's conserved. You can also sneak this guy in. Okay, so anyway, so that was just a quick explanation as to why this is indeed an invariant measure, but maybe you can also just believe me on that.
What is theta again?
Sorry?
What is theta?
Delta?
Theta.
they're two free parameters. So I have a 2-parameter family of measures. I can tune them as I wish. Okay, so for any beta and theta, this is invariant. Yeah, any further questions? Okay. So let me start by just explaining a very sort of a shadow of the framework that I actually want to tell you about. So an asymptotic shadow. So this is going to be an asymptotic result that you can prove about the total lattice under that under this invariant data. So what we'll do is we'll run the total lattice for some time t, which is much bigger than 1, under the thermal equilibrium from the previous slide. And I'm going to let n, the number of particles, be much bigger than t, as I kind of indicated before. I'm going to normalize. I'm just going to shift do a global shift of the particles so that the middle particle is at 0. Okay, just because I don't want to have to track it. So yeah, let's just make the middle particle at 0, so we're kind of symmetric. A technical assumption that I'll need that won't. I mean, it should be necessary, but for the proof of this, it's needed. Is that we'll assume that the theta parameter, this theta, is sufficiently small. Okay. Yeah. Okay, so the theorem is the following. So the following hold with very high probability after time t. So I can look at this total lattice. It's a dynamic under these particles, and I can ask myself how many particles. What is the net number of particles that cross the origin? Right. So some number of particles are crossing the origin from left to right, and some are crossing from right to left. So you do left to right minus right to left. Right. So that's like the net current past the origin. Okay. And the claim is that this will be order t. This will be at most of order t to the 1/2. Plus some lower correction. Okay, so it's almost diffusive. It's at most diffusive. Okay. The second thing I can ask is the net momentum across the origin. So I again look at particles crossing the origin, and every time a particle crosses from left to right, I add its momentum. It's p. And every time it crosses from right to left, I subtract its momentum. So I subtract p. So this is kind of the net momentum crossing the origin after some amount of time. There'll be some explicit constant m, which is explicit in terms of m and in terms of beta and theta, times t, so that will be kind of the first order term. And then again, you'll have some diffusive corrections. It's a t to the 1/2 correction to that, plus a little 1. Okay, so this is these are two asymptotic results that you can prove about the total lattice at this thermal equilibrium. Okay, and I should mention sort of there are some aspects of this result that are natural and some that are maybe less obvious. So the first thing is that the constant is not so difficult. These constants, there's actually like a 0t here. Look, the law of large numbers, the t term here is kind of 0 here. That's very natural to expect because the total lattice is kind of symmetric, and the distribution, the initial distribution is also symmetric. So I should imagine the net change across the origin to be 0 just by symmetry, right? Crossing left to right is kind of equal from crossing of right to left. So from that point of view, the fact that this should be the fact that the leading order term should kind of be 0 is something that you might be able to guess. The fact that it's, or at least an expectation that it's 0. The fact that it's 0 with high probability, and more specifically that you get this exponent is in my view less obvious. Yeah.
The potential is not symmetrical.
Yeah. The symmetric is not obviously symmetric, but there is a symmetry. There is an implicit symmetry behind it. You can kind of
the asymmetry of the potential is suppressed by this limit that you're taking.
I think it's more like you can just negate everything in sight, and it will have a symmetry like that.
Because you have a qi minus qi plus 1, but you also have a qi minus 1.
Yeah.
I guess
That's where the I was wondering the same.
If you negate everything, it will be symmetric. Yeah. So okay. Yeah. Okay, so this exponent is kind of less obvious, and in fact, it's believed to be optimal. So it's believed by the physicists that this exponent t to the 1/2 plus the law of 1 is believed to be the best you can do, and that the fluctuations will Gaussian. And in fact, if you follow these proofs very carefully, you can almost fish out the Gaussian. You can. I mean, I didn't quite do that, but you can see heuristically from the proofs that a Gaussian like this will come about. Okay, so now, as I said before, these
sorry.
Yeah, please.
A basic question. So this was for large numbers of particles, but just to appreciate what the system is, if I just have 5 particles.
5 particles, yeah.
What happens when it runs? Do they just shoot off to infinity?
They will shoot off to infinity in different directions.
Okay.
Yeah, so I'll have 5 particles, and one will go to infinity here, one will go to infinity here, one will go. Yes.
You're in dimension 1, so.
Oh, sorry.
Yes, okay, but they're going to shoot away from each other.
Yeah, I mean, I'm looking at this is time t equals 0.
Okay, it's not clear from the formula.
This is t equals
I see what you mean in the phasors.
something like this.
Okay, thank you.
Yeah, that's what will happen in just five particles. Yeah. Any further questions? Okay. Okay, so all these asymptotics are consequences of sort of a broader perspective that interprets the total lattice as a soliton gas. So I want to explain this broader perspective because I feel like understanding that broader perspective, once that perspective is kind of understood, these are very quick consequences of it. And that broader perspective is believed to hold some sort of great generality, which is, to me, what attracted me to this family of questions in the first place. Okay, so let me start by explaining. I mentioned the word soliton gas. So let me start by telling you what a soliton is. Okay, so the total lattice, and this is one of the first observations of Toda when he introduced it in the first place, is that it exhibits so-called soliton solutions. Okay, so these are locally, broadly speaking, so heuristically speaking, these are locally wave-like solutions that are kind of like localized in space, so they look kind of like waves, and they're functions that kind of retain their shape as they evolve. Okay, so there's an explicit form for one of these soliton solutions for the total lattice. It takes the form Qn of t is equal to a logarithm of a certain quotient. So it's 1 plus something over 1 plus something, where that something is given by an explicit exponential. Okay. So this exponential is dependent on two parameters, lambda q, which I have the ability to tune as I wish. Okay. So I'll have e to some constant dependent on lambda, which I've hidden from you. It's explicit, but I won't write it down, times n minus lambda t minus q times some constant in front. Okay. So that is the basic form of this fn lambda t of q. Okay, so that's going in the numerator, and then in the denominator, I had the same exact thing, but where n is shifted by 1. Okay, and you can convince. So this is going to be an explicit formula for some value of Qn of t, and you can convince yourself, and Pn of t, as you might imagine, is simply the derivative of n t of this object. Okay, as the Hamiltonian dynamics demand. Okay, and you can show by computation basically that this is a solution to the total lattice if I ring my A and B properly. Okay, now let me plot this thing. Okay, so I'm plotting Qn of t in n. So this is, you should think of this as n, and this is the x-axis, and t is just fixed. So t is, you can take it to be 0 if you like. Okay, and I'm actually not going to plot q, but I'm going to plot the differences in the q. So q at n minus q, n minus 1. Okay, and if you do that, what you can see is that q will basically be localized. It'll be localized around this site n is equal to, it'll be localized basically where this exponential is 0. And after that, it will just fall off exponentially. So we'll have this kind of wave-like, it'll have like a kind of this localized shape to it. Okay, and now as I evolve in time, this peak will just start moving forward at a certain speed. Okay, and that speed, you can imagine, I mean, it's going to be just lambda. Okay, and you can think of the location. The location of the wave is kind of the location of this peak, which will simply be lambda t plus q. So this peak is kind of just moving forward at speed lambda over time, and its initial position is given by this capital Q. Okay, so that's an example of a solution to the total lattice that just, you know, it's kind of, it's almost a wave that just keeps kind of pushed forward in time. Now that's one example of a soliton solution that has one soliton. There are also multiple soliton solutions, which you can imagine as kind of superpositions of solitons. Okay, and one way of saying this is that they exist. You can also write down what they are. It will get a little bit messy, but if you want to know like kind of structurally what you do is that you swap out this fn of t here with the determinant, an m by m determinant if I want m solitons. So if I want just 2 solitons, this would just be a 2 by 2 determinant. So you swap out this guy with the 2 by 2 determinant, and you swap out this guy with the same 2 by 2 determinant where you just increment n. Okay, and this will give you a new solution to the total lattice, where now you have to rig A, B, and C properly. Okay, and for any m, you can do this. But more important than the form, like kind of the exact form of it, is maybe the shape of how it looks like. And what it will kind of look like if t is big and t is small, is at least if m equals 2, and you can imagine what will happen for more m's, is that it will kind of look like 2 solitons that are far apart from each other. And these two solitons will move almost as if like each one were moving independently until they get close to each other. And when they get close, they'll start to kind of interact. There will be some non-trivial way in which they transmogrify, and they have some bizarre and messy, intricate interaction with each other. But after that, they will separate again, and into something that looks like this. And what will happen is that the original shapes of these solitons, the original speeds, the lambdas, and their widths will their heights will be the same as before. Okay, so that's what I meant when I said that that's another manifestation of retaining their shape as they evolve. If they pass through each other, so basically, if two solitons pass through each other under this solution, then they look as if they did before. Okay. So after an intricate interaction, the solitons retain their shape, but they undergo a so-called scattering shift. So as I said before, a soliton has a position which is basically given by this Q. In general, it'll be given, the first soliton might have a position Qi, and the second might have position Qj. Okay, and if the soliton were moving in the absence, like if this soliton were moving in the absence of this one, it would just move forward at speed lambda 1, say. Okay, now in this case, when I've added the soliton in, it will reappear. It will eventually kind of, after it's done its interaction with the new soliton, it will appear in its original form, but its location will be different from if it were just moving at speed lambda from the beginning. So when it passes through the soliton, it will behave as if it moved at speed lambda, and then we're shifted by a so-called scattering shift, so we'll get kind of translated after it passes through the soliton, and then it will move at speed lambda after that. So basically, every time a soliton passes through another one, it undergoes just a shift. Okay, and likewise, this soliton, once it passes behind this one, it will also get shifted back by lambda, by the scattering shift log of lambda I minus lambda j. Then
Yeah, can I ask, what is it? I think I've missed something here. What does it mean to say that wave is a solution to the total?
Okay, so this is an explicit form of Q, right?
Yeah.
Okay, and I can differentiate it, and that'll give me P. Like, just take its T derivative, and that'll give me P, right?
Okay.
And this P and this Q, I define a P and a Q for all n and t. The claim is that solves that P to E from before.
Okay.
Yeah, so like that P and Q just satisfy this P to E.
Oh, okay.
Yeah. Yeah.
And then what is that a picture of?
This is a picture of this plot is a plot of Qn minus Q of n minus 1. So I'm plotting the gaps actually between the Qs. And this x-axis is n, and the y-axis is the gap Qn minus Qn minus 1, or this value basically. And I fixed t. So just think of t equals 0.
Okay.
And each plot is a new value of t. So like this is maybe t equals 0, this is t equals 10, this is t equals 20.
And this is a probability density.
This is not a probability density. It's just the plot of Q. I mean, Q is a function of n and t, right?
Oh, okay. Yes.
Imagine t is 0, so it's a function of n, and this is just its plot in n.
Okay.
Yeah, does that make sense?
Yes, thank you.
Any further questions? Yeah.
Excuse me. So, what is a scattering shift? Is this a piece of time, or is just the difference between the out shape and the in shape?
It's not the difference between the shapes. It's the position. It's the difference between their positions. So what you have this original soliton, which is moving at speed lambda. Okay. Now I have a soliton here, and I have a kind of another soliton, and this soliton will move forward at speed lambda originally, but then it will start to mesh with the soliton according to some very bizarre interaction. But after it meshes, it will reappear, and it will look as if it did before. Okay. So now the claim is that the position of this soliton at time t, so this position at time t, so let me call it Q of t, will be Q of 0, so its initial position, plus lambda t. That would be if we were just moving straight at time, just straight up at velocity lambda. But then I'm saying that in addition, because there was this additional soliton, there's an additional shift. And that shift is the scattering shift. Okay, and the shift is happens to be given by 2 log of lambda I minus lambda 1 minus lambda 2. So basically the claim is that whenever one soliton passes through another one, its linear evolution kind of gets shifted a little bit by this quantity. Okay, yeah.
Does it mean that it's kind of, you're thinking going slower while it's interacting and then going to the same speed afterwards?
Well, so this shift will be positive and this shift will be negative. So one speeds up and one slows down maybe, but yeah.
According to the optical.
Exactly. Precisely. Yes. Yes. Any further questions? Okay. So moral is that when two solitons interact, they're far apart. They're nice. They go linearly. When they interact, it's very messy. But after the storm ends, they are very nice again. But after a shift, that's explicit. Up to but the positions are just shifted, which up to an and the shift is explicit. Okay. Good. Now. Okay, so that's what happens if I just have two solitons or a finite number of solitons. They kind of they separate. But now what happens if I have a very rough initial data? So the broad belief is that integrable systems. So this was I remind you that this discussion was for an explicit solution. I was always taking explicit solutions, but the belief is that if I take an integrable system under generic rough or random initial data, I can think of this as a dense collection of solitons. So this is somewhat imprecise, and my goal in this talk will really be to make this precise. Okay, and but broadly speaking, what should I imagine as happening? So I have my integrable system. Okay, like the Toda Lattice. The Toda Lattice has its variables p and q. I should be able to take a state of this Toda Lattice, so like a given vector of momenta and position state, and spit out some soliton data, lambda I and qi of t. So I should be able to spit out a bunch of variables, basically, lambda I and qi, where lambda I you should think of as the amplitude or the speed of the ith soliton, and qi of t you should think of as the position of the ith soliton, okay? And just to give you a sense why this is not trivial, if I were to take this picture, it's very natural what the two solitons are. I mean, here might be the qi, like here's the obvious location of the first soliton. Here's the obvious location of the second soliton, and just the speed at which they're moving are going to be the lambda 1 and lambda 2. If you were to have an initial data like this, it's much less obvious how to decompose this thing into a bunch of solitons. Okay, so this is this is what's believed to basically be the case. You should be able to decompose this into a bunch of solitons. Okay. Okay, so good. So one is you can just cook up some definition of what these solitons are. That sort of superimposed. You could think of this as some so that kind of superimposed to form your initial data. Okay. The second is that this is useful. Okay, so you have many quantities of interest for your original integrable system, and the claim is that they can be approximated in terms of the soliton data. So there are many. This is actually so there are many quantities that you might be interested in, and the claim is that most of them, or basically all of them, can be approximated by the soliton data. But just to give you an example of what I mean, for example, if I take an interval I, the number of Toda particles, so the number of q's, the number of q's basically, in I should be equal to the number of solitons in I. Okay, so from that point of view, there's kind of a if I ask any question about how many Toda particles, how many q's are located in a specific interval, that reduces to a question about how many solitons are in a specific interval. Okay, so I can reduce questions about the Toda lattice to questions about the soliton system. Okay, which is at the moment kind of fictitious, but one indicates that it should be there. Okay, so now that's great as long as I can actually understand the soliton system, right? So that's 3. Okay. So 3 is that I know how the solitons evolve, okay? And they evolve approximately according to what was indicated here. But let me write down the equation and I'll explain the relation between this. So the claim is that the decayed soliton, it evolves, it satisfies this equation here, which is that qk, the location of the decayed soliton at time t, is equal to its location at time 0 plus the velocity lambda k t. So this is kind of the natural linear flow. But now I'm adding and subtracting a bunch of these shifts, these scattering shifts. Okay, and I remind you for the Toda lattice, the scattering shift is 2 times the log of x minus y. Okay, so that's the same from before. Okay, now let me give you. This formula might not mean much on the outset. So let me tell you what the interpretation is. So in the absence of these two sums, the interpretation is that the j soliton is moving just linearly with velocity lambda j, right? So that's all this is saying. Okay, but the difference is that when one soliton meets another one, this location will instantaneously move forward or backwards by this s lambda k lambda I, depending on whether the j soliton meets like qj meets qi from the left or from the right. Okay, so it's kind of like this thing is happening everywhere at the same time for all the solitons. Is what this equation is saying. Okay. Yeah. Okay, so I mean, I stated this as basically an interpretation of this. If you work through a few examples, you'll convince yourself of that. But it won't be. Yeah, I mean, going from here to here and back is a little bit of work, but not. It's kind of unwinding definitions basically. Okay, so this was predicted originally in the physics work of Zakharov around 55 years ago. In the case of a classical integrable system called the KdV, or Korteweg-de-Vries equation, he was looking at a case when the spacing of the particles are pretty far apart, and if the spacings of the are the sort of not the particles but the density, the number of Qs you can think of is very small. So in that case, actually, this is very natural because what you might imagine is that you will have some initial data that might look something like this. Okay, and these solitons you should imagine as being kind of far. If there are not many of these particles, then the solitons should also be kind of sparse, and in which case you should imagine that they basically only interact in pairs. And I just told you how the pair interaction works, right? It works basically like this. Okay, so in the dynamical cases, it's fairly natural. It was later predicted in the physics work of Bertini, Kalura, Donatis, and Fagotti, and independently by Castro, Alvaredo, Aldoyan, and Yoshimura, that this is still true in the dense case. And now it's much less obvious. I mean, in fact, it was a lot of people. I mean, various people saw this originally and thought, this is way too optimistic to be true. Yeah.
So I'm a little bit confused. The statement is about the initial conditions or about solutions to the evolutions of the integrable system?
So the first two are just statements about the integrable system, are just statements about any state of the integrable system. So the first statement is that given a state of the integrable system, I can tell you what solitons are. The second is that this is actually telling you something about the original integrable system. So these two have nothing to do with dynamics at the moment. The third is telling you how the solitons evolve under the dynamics.
The initial condition can be anything, whether the system is integrable or not.
Yeah, well, so I mean, the belief is that this should only work if the system is integrable. Like this, you can only do these tasks are only possible if the integral. Like, you can only accomplish 1, 2, and 3 at the same time if the system is integrable. So the integrability, of course, comes in 3, right?
Yeah,
in fact,
yeah.
yeah.
Okay,
Yeah, but 1 and 2 on their own are kind of useless. I mean, like, yeah.
Because it's just the initial condition.
Yeah, exactly. It doesn't mean anything. Yeah. So yeah.
So it means in a sense that the solitons form a complete basis.
Yeah, but the soliton, I should say, the dependent. It's not like I give you any. The choice of solitons might depend on the choice of integrable system.
Yeah, for sure.
Yeah. So for now, they form a basis, and in fact, that's often how they describe it in the physics literature. They say that this is a new and very convenient basis for analyzing the systems. Yeah. Okay. Any further questions? Good. Okay. So So now the goal of this talk is to give some kind of perspective on how you might justify some of this framework for the total lattice at thermal equilibrium. So now to do that, before I do that, I want to quickly mention a few previous works around this topic. So I talked about the total lattice. There, of course, there's this whole zoo of integrable systems that I didn't even mention. There are many of them, but there are certain combinatorial integrable systems that are a bit simpler than Hamiltonian ones. Two examples are, I won't go into exactly what these are. I mean, you might have seen them or you might have not. I won't mention these later on. I just want to give you a sense of what has been done before. One is the hard-rod model, which is also known as the one-dimensional hard spheres model. And another is the so-called box-ball system. So this is a cellular automaton. This is a deterministic cellular automaton. So in both of these, these are both examples of combinatorial integrable systems that have some simplifications over kind of Hamiltonian ones. And in both of these systems, there is kind of a well-defined map from the system to the soliton data. So that map, the first map I defined, always exists and is precisely defined. And once you define that map, this equation, okay, so once you define that map, then 2 kind of falls out, and 3 holds not approximately, but actually exactly. So this is not even an asymptotic phenomenon. This is just on the nose for any system. For any finite number of particles, you will have this. Okay, so Okay, and for other integrable systems, for kind of Hamiltonian ones or dispersive PDEs, there's a wide set of them. This map is rarely actually it's not really understood, or it has not really appeared. A precise definition of this map has not really appeared in the literature. And so what people do is they go back to kind of looking at specific solutions. So there are many specific solutions that you can study, and the broadest class of them, a fairly broad class of them, are called finite gap solutions. So these were introduced in the Novikov school in the 1970s by Dubrov and Novikov. It's Matvey and Krishever, and these are kind of generalizations. You can think of these souped up generalizations of this M-soliton solution that have many parameters in them. They're algebraic geometric in nature, so they're associated with an algebraic curve, basically. And these are many soliton solutions of these equations, and you can try to. And the advantage of these solutions is that they have many parameters, and good candidates for soliton locations, which, as I said, is kind of the drawback here. You might not know how to define them a priori. Good candidates for soliton locations are kind of incorporated into these solutions as parameters. Okay, so at least now you can define them as just parameters of these specific solutions, and then you can try to take scaling limits of these solutions, like take the number of parameters, which basically involves taking a hygienist limit to infinity, and you can try to see what's happening to these solutions after a long period of time, and try to fish out an equation of this nature. Okay, and signatures of this have been attempted and to some extent done in certain special cases in the works of L. So this is in the physics work of L, and also in the mathematics work of Girotti, Grava, Jenkins, Miller, and McLaughlin. So there are kind of two difficulties here. The first is that taking a scaling limit of these solutions often tends to be fairly complicated, especially if the genus of this curve is big. And often you actually want the genus of this curve to be big. And the second difficulty is that this whole framework basically takes a specific solution and analyzes it. But what you might actually be interested in is starting out with a natural initial data, like the thermal equilibrium, where I just distribute my P's and Q's according to Gaussians or gamma or basically Gaussians or chi-random variables, and see what's going on there. And in that sense, this framework doesn't really tell you. It's hard to find a solution that kind of matches with that one. Okay, so I'll try to give a different approach to these types of questions. Okay, so to do that, I need to now talk a little bit more about the integrability of the Toda lattice. Okay, and this goes back to around 50 years through the work of Flushka. So let me tell you the sense in which the Toda lattice is integrable. Okay, so as I said before, as I hinted at before, when I mention integrability, it means that there are many conserved quantities behind the system. So let me tell you what those quantities are. So remember that I had this Toda lattice, which were these P's and Q's, positions and momenta and positions, and I defined these A's, which were the exponential. So these AI's were So it's the difference, it's the gaps, okay, so this is AIT. So this is just some explicit thing. It's basically e to the difference, e to the gaps of the Q's over 2. Okay, so what you first do is you set up a tridiagonal matrix of this form, where you put the momenta along the diagonals, and along the off diagonals are exactly these A's. Okay, so that's going to be a matrix here, which is this L of T. It's sometimes called the lax matrix. And so this is an n by n matrix, okay? And this depends on T, right? Because all of these A's and P's, they depend on T. So this matrix is evolving over time, right? Okay, the statement that's due to Flushka back in 1974 is that under the Toda lattice, so if I evolve these P's and Q's and therefore these P's and A's according to that PDE, the Toda PDE, then the eigenvalues of this matrix don't change. They're preserved. Okay, so I have a matrix, an n by n matrix, all of whose eigenvalues are preserved. So I have a lot of quantities that are fixed or preserved throughout these dynamics. Okay, and that is what I meant before by the integrability of the system, that I have n conserved quantities from n particle system, and that turns out to be as many as you can get. Okay, so that you have a maximum set of conserved quantities. Okay, so these are so we have these eigenvalues. Okay, and now using these eigenvalues, the first step of this whole program was to define the soliton data, right? The amplitudes, the velocities, these lambda i's and the qj's. So it's been understood for a fairly long time that whatever reasonable definition you might think of for the lambdas, for the amplitudes, and it better be these eigenvalues. So by definition, just set the lambda i's to be the soliton amplitudes, the soliton velocities. Okay, so that you can think of that as definition. And people, physicists, mathematicians kind of understood this for a very long time. Less obvious, as I said before, are the locations. Okay. But there's a natural thing to do, okay, which is that if I'm telling you that the eigenvalues are the kind of the amplitudes or the velocities, why not look at the eigenvectors, right? So we can now try to use the associated eigenvectors to define the soliton locations. And if you know a little bit of quantum mechanics, this is very natural because if I have if I have some wave, some state, some wave in a quantum mechanical system, the position is going to be the position associated with it is going to be a random variable whose probability of being equal to an index k is weighted by the square of the kth coordinate, right? So you can try doing something very similar here, and that will be exactly what we'll do. Okay. So now, in order to explain that more precisely, let me tell you how the eigenvectors of this matrix look. So I'm going to take this matrix before. As I said, its eigenvalues are the soliton amplitudes. I'll be interested in its eigenvectors. Okay. And the claim is that if I look at this Lax matrix L, and look at any eigenvector of it, so any eigenvector of L, I'll call it uj. So uj has n coordinates, uj1, uj2, all the way to ujn. The claim is that these will be exponentially localized. Okay, and what that means is that there exists kind of a center, a localization center, which I can draw it. So here these are the and then here I'm going to plot. Here I'm plotting U. So there will be some localization center in which away from which the eigenvector will decay exponentially. So there'll be some point phi here, where maybe say the eigenvector has the maximum mass is at this entry phi, and then away from that it will fall off exponentially. Okay, so that's so this is now a random matrix statement, right? Because I'm taking this matrix L from my previous slide and I'm putting in that thermal equilibrium, right? I'm sampling these A's and these P's according to these Gaussians and chi-random variables, right? So now this becomes a random matrix, and the claim is that with very high probability, any eigenvector will be localized and will have a picture that looks like that. Okay. Okay. So this result goes back quite some time. I mean, the original works kind of in this direction were due to Molchanov, and results more in the nature of what I just said were due to Consuliard and Shankar, and they were first developing this theory in the context of one-dimensional Anderson localization. Okay, so now my point is that if you take in any eigenvector of this matrix, it's basically going to live on just a few coordinates, which are close to this phi. So I'm just going to call this phi. I'm going to call phi basically. I'm going to set little phi t of j to be any index such that uj phi of t is not too small. Say, I mean, this constant is somewhat arbitrary, but you can just say that it's it's not exponential in n. Say, I mean, so just something that's not too tiny. Okay. So this index phi, so as I said before, this index phi you should think of as basically this capital phi here. Okay. Yeah. Okay. And now this you should think of as kind of more or less the particle index of the soliton. So I'm going to biject basically solitons to particles. Okay. So for any, Toda Lattice has many particles, n particles, which are these q's. Okay. This phi here is going to be the index of the j soliton. So I'll say that the location of this QJT is equal to the location. This is kind of the location of the J soliton. This is equal to the location of the phi jth Toda particle at time t. So a picture you might have in mind is the following. So you have these Toda particles. These are the QIs. Right? Okay. And then I'm just going to scramble them, and I'm going to define. This might be Q1, this might be Q3, this might be Q2, this might be Q5, This might be Q4. Okay, and then this depending on where the associated eigenvector is localized, I will define the Q's accordingly. So that's kind of an exact match between the Q's and the phi's. Okay, so this is just going to be my straight definition for what the soliton locations or soliton positions are. Okay. And again, okay. So you should think of phi t of j as the index of the soliton with frequency or amplitude lambda j, and you should think of qj of t as its location, as its position. Okay. So now I've defined the soliton data. I've taken my positions, my p's and my q's. I've cooked up this lax matrix. Its eigenvalues are the frequencies or the lambdas of the solitons, and the q's, the capital Q's, which are determined by where these eigenvectors are localized, are telling me what the locations of these solitons are. Okay, so I've basically taken my Toda data and spat out a family of soliton data. Now, at first, this might seem kind of arbitrary, right? What does this actually have to do with the peaks and the troughs of the Toda Lattice itself? I will try to. I mean, later on, I'll basically show that the remaining two properties that were demanded of the soliton decomposition are actually theorems. Okay, so I should say that there's a question of uniqueness here. I mean. I've defined phi j to be any index for which this is not too small, but since this uj decays exponentially, there are only a few indices for which it's not too small. So you can quickly check if you know that these localization centers are basically unique up to a very small error that won't matter up to asymptotics. Yeah.
One is more general. So this exponential localization works only for the, maybe you said before, but I missed it, only for the Toda Lattice, or it's seen as a more general statement about random matrix?
So it will hold for any tridiagonal random matrix with IID entries, say, or entries that are random with some decay of correlations. So if you have just a random tridiagonal matrix whose entries are not necessarily exactly independent, but at least don't correlate very much, I mean, have kind of decay of correlations, then you'll have this exponential decay of correlations. So it's a fairly general statement. Yeah.
The second thing is that then you're sending n to infinity at some point?
Sorry?
You're sending the number of particles to infinity.
And yes, it's a high dimensional matrix. Yeah.
It's not too obvious. So like, because you want to choose the constant in a way that you're singling out, but when you send n to infinity, could it be that, I mean, you're trying to fix n,
Yeah.
but n also is going to infinity?
Yeah, right. So I mean, okay, so let's say if you have a function that's decaying exponentially, how far can you go before it reaches a power of n? You can only go log n.
Yeah.
So there will be an error, there will be some kind of, I mean, you might not be exactly equal to this phi, but you'll be off by it by most log of n, which is very small in comparison to any power of n. So I mean, you will be off slightly by something that grows with n, but it'll be very small. It'll be like logarithmic as opposed to a power. Yeah. So from that point of view, it's basically unique, and that basically will be enough for any kind of asymptotic statement that you want to prove. Yeah.
Will each particle have an associated soliton?
Yeah. Oh, so you're asking if this is a bijection?
Yeah.
Because I mean, at the moment, I've kind of said that any soliton is a particle. Right now, you might ask, is any particle a soliton?
Yeah.
Yeah. Okay.
Or
And
at least up to log n.
yeah, correct. Yes, it is. It is. Yes, indeed. Yeah. So there is a bijection. That's a bijection up to log n. Yeah. 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 Any further questions? Okay. So now I can try to state some theorems. So now, okay. So now I'm again going to take my Toda Lattice under thermal equilibrium. I'm going to run for a long amount of time. Okay. So as I said, there are two statements that you might want to know. The first is that you can express the Toda Lattice quantities using solitons. Okay. So actually, basically, just due to the question that that Mitchell just asked, since Toda particles and solitons are bijection, it's very natural to think that if I have an interval, the number of solitons in an interval is equal to the number of Toda particles in an interval. As I said, there's just bijection between the two. Up to a small error, this is a bijection. So that statement is kind of immediate. So in this proposition, I try to give you an example of a slightly more, a somewhat less trivial statement, which is that in any interval, I might ask for the total Toda momentum. So I take some interval and I look at all the Toda particles in the interval and I ask for the sum of their momentum. So you could think of this as kind of the average momentum in interval. And this is equal to so the statement is that this is equal to the total soliton amplitude in the interval. So so that's the left side. This is the left side of the total Toda momentum. The right side is I look at all the solitons in this interval. So I, so that Qi of t is an I, and I sum up all their lambdas. Okay. And the claim is that these two are equal up to something up to something that's kind of small. Okay. So from that point of view, if I care about any kind of if I care about basically the momentum of the total lattice, I can also compute that using the soliton data. Okay, and this is just one approximate. This is just one kind of correspondence in an infinite hierarchy of them. So there are an infinite number of statements of this nature. Okay, so from that point of view, basically anything you want to know about the total lattice is expressible in terms of the solitons.
Do you mind just putting this in context? So you said so Moser and so there were those early results from the 70s that say, I thought they already had interpreted the lambdas as the moment.
Yeah, I think that they were more saying that for any reasonable definition of what you might give for these lambdas, they had better be the eigenvalues of this lax matrix. So in particular,
but not relating it back to this moment.
yeah, exactly. That's correct.
Oh,
Yeah,
okay.
that's correct. Yeah. So in particular, in order to have a relation like this, you need to define the soliton locations, right? And that wasn't there back then. Yeah. Any further questions? Okay, now, so this is a statement. This is that you can put this using kind of random matrices that are somewhat known in the context of Anderson localization. The somewhat deeper statement is the scattering statement, which is telling you how these soliton locations are evolving in time. Okay, and the statement is that what the prediction I had before is basically correct. Ignore this alpha. I think this alpha might actually end up just confusing you. So this alpha is, yeah, okay. Imagine the alpha is 1. Okay, you won't lose anything by doing that. So what it's saying is that qk of t, the location of this k soliton, is exactly what I had predicted from before. It's the linear kind of evolution of the original thing plus. Okay, ignore the sign. You have to add it as a technicality, but you won't lose anything if you just ignore it. And it's this sum of this kind of difference of scattering shifts. And it's almost exact once again. The error here, it's not going to be exact, but it's almost exact, and the error is going to just be some power of log n. Okay, so from that point of view, not only are the solitons do you have a relation like this, but it's I mean both of these statements are true up to a tiny error. So that means that even if you want to analyze the total lattice, this piece, to a very small error, the solitons are still sufficient to do that. Okay. Yeah.
So the concept of the theorem is basically understanding how the error evolves in time and checking that it's still log m.
Sorry?
The statement of the theorem is basically checking that. I mean, once you map the soliton into the particles into the solitons, you know how the solitons evolve. You just have to track how the error evolves.
Well, I don't know how the solitons evolve. Under this definition, I don't know how the solitons evolve.
Okay.
Right? Because originally I had given you these pretty pictures that were defined by explicit solutions. So the definitions of the solitons there were just the parameters in those solutions. Here I defined these solitons just according to these eigenvectors. So understanding how now that's a completely a priori different definition. So you now you actually need to work to check this kind of statement. You have a completely different definition of what the soliton locations are, and you actually need to prove that they evolve in the same way that you expect them to. Yeah. Okay.
So the statement is only about large n?
Yeah, this will only be true as n becomes large. It's not exact. If you take n to be 5, it will no longer be true.
But the expectation that you
that was also for large n. You can't expect that to be true for small n.
okay.
I hid that in terms of an approximation. That approximation is true for large n. Yeah. All of these statements are going to be asymptotic.
But I guess in the limits in which they are far from each other in success, you recover the other results.
Yes, you do, exactly. Yeah. So this will give you a new proof. This actually, if you work a little bit with this, you can reprove most of this result.
Okay.
Yeah. Okay. Now, before I conclude, let me just give you one one thing you can kind of do with this whole framework. So you can show. You might ask, okay, I have now these solitons. I can ask, how do they evolve? This gives you an approximation for what's going on, right? Or some basically equation for what's going on. But you can ask for an asymptotic, like how this is still an equation. It's not a totally trivial one. So I can ask myself, what is the limiting behavior of QKT as t tends to infinity? So the statement which you can prove by analyzing this equation basically is you can prove that this QK of t, it evolves almost linearly. It will have a speed which is I call VF of lambda k plus some error, which is again kind of t to the 1/2. So this t to the 1/2 is the source of the t to the 1/2 I had from the asymptotic slide from about half an hour ago. And this t v of f, it should be thought of as kind of the effective speed of the soliton, because as you might imagine, the solitons, they're moving kind of linearly, but then they're getting bumped around by all of these terms. So the velocity of these solitons might not be lambda k anymore. They might change because of this huge shift that is constantly undergoing. And that's kind of incorporated into this VF of lambda k, which is not going to be lambda k, but it's going to be something explicit still, which you can actually compute. Again, the explicit form was predicted in these physics works, and this theorem kind of confirms that. And using this theorem, you can go back and prove those previous results I'd mentioned before as just very, very quick consequences. Okay, so I was going to mention a bit about the proofs, but let me just stop here. So the summary is that the belief is that it should be possible to interpret many integrable systems under random initial data as soliton gases, which you can think of as dense collections of many solitons. And they're useful because quantity for the actual system that you were originally studying can be nicely expressed in terms of the soliton data. And you can actually analyze the soliton data. They evolve according to an asymptotic, a certain scattering, this equation I had written down before. And we analyze this for the total lattice at thermal equilibrium, and we explained that the soliton locations are given by kind of localization centers for the eigenvectors of the Lax matrix, and the soliton frequencies or velocities are given by the eigenvalues. And then using that definition as kind of a bare definition, we can establish these two statements. Okay, and the proofs, I didn't get to use them much, but they use ideas from random matrix, tridiagonal random matrix theory, in particular exponential localization of Lax matrix eigenvalues, and I didn't quite get to this, but you have to actually not only know that they're localized, but understand their rate of localization, which is expressed through a quantity called the Lyapunov exponent. Okay, and you can actually use this to analyze asymptotics of the total lattice and its solitons. So with that, I'll thank you.
Questions?
So these Lyapunov exponents for the localizations.
Yeah.
It's great. Are those dependent on the distribution of the entries?
They are, yes. So in fact, I can tell you. So it's called the so-called Dallas relation. So this exponent is the rate of exponent, that rate of localization is sometimes called gamma, and it has a form. This form is given by the expectation of the log of the entry. So off the bat, you see a dependence on the entry. And then you also have a dependence on the density of states. And this density of states also depends on the entries of the matrix. So it's not like the Wigner case, where it's independent of the entries. If you have a tridiagonal matrix, the limit shape will depend on its entries and the laws of its entries.
And this row of lambda is explicit?
It is explicit, but somewhat complicated. It's nowhere as clean as the Wigner semicircle or custom decay or anything like that.
And am I right in saying that the randomness of the initial data is just to show certain facts about this random Lax matrix, like eigenvector deal?
Yeah, so there are two things you need. Okay, so yeah, so first of all, yeah, so basically you just need, for that, yeah, so you need just to show properties of the Lax matrix, that's correct, and to show its properties under the evolution of the total lattice. So I not only need it to be true initially, I need it to be true after a long period of time. So that's actually why I need to be at equilibrium, because if I know it's true originally, if I'm at invariant measure, then it will be true after a long period of time by definition, basically. Yeah. So yeah.
For the eigenvalue, they have Poisson statistics? Or...
Sorry?
The eigenvalue.
They have Poisson, yes. They have, I don't need that, but they do, yeah.
Any other? Actually, why exactly does it fail for finite? I don't know. Maybe let me make it more precise. What part of the expectation fails? I mean, is it why is it not true that for finite n, solitons will still be a complete basis?
Well, you have to define them now, and this definition, this approximation, I mean, people would expect it. I mean, this error should have something to do with n. Like this, I mean, if it had nothing to do with n, this would kind of be exact in some sense.
Right, so maybe it's harder to find solutions, but...
Sorry? Well, I think you have an initial problem of how to even define the solitons, which is not clear. But even after you do that, I think it's too much to expect this thing to hold exactly. And I don't think people really thought that that should be true. So you need some kind of parameter going to infinity so that you can even make an approximation, you can make sense of an approximation. And for that, the natural thing to do is let n go to infinity. Does that partially answer your question?
Yeah, maybe I can ask you.
Yeah, okay.
Can you use beta as a parameter?
Sorry?
Can you also use beta as a parameter?
For
this dense limit or whatever?
yeah, I mean, so beta is free. So these results hold for any beta. All these results hold for any beta. So that can be chosen as you wish, I guess.